Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the conditional mean function, which is a very important concept in applications such as regression or causal inference. The conditional mean function encodes the average of an uncertain quantity given the value of a related quantity. Let's get to it. Our goal is to define the conditional mean function and also to explain how to estimate it from data. So the question is, imagine that we have two random variables A and B in the same probability space or in the same probabilistic model, and the value of A is revealed to equal a certain fixed value. All right? Then what is the mean of B? That is the question that we want to ask. Let's take a look at an example. So here we have two discrete random variables, A and B. Each of them can take three values, 1, 2, 3. And 1, 2, 3. And what I'm showing you here is the joint probability mass function, which tells us the probability that A and B take certain values at the same time. So for example, the probability that A is equal to 1 and B is equal to 2 at the same time is equal to 0.2. Now imagine that A is fixed to a certain value. So for example, A is fixed to equal 1. Then the relevant values of the joint PMF are those for which A is equal to 1. Remember that in order to characterize the behavior of B when that happens, what we do is we take those values and renormalize them so that they give us the conditional probability that B is equal to each of its possible values when A is equal to 1. And that is achieved by dividing this slice. So this slice is equal to the joint when A is fixed to equal 1. The way we normalize it is by dividing by the marginal probability of A being equal to 1. Why? Because it's the sum of those guys. So when we divide it, we ensure that things add up to 1. This is just like a crash review on conditional PMFs of discrete random variables. If you don't remember this, go to the video on conditional distributions of discrete random variables. Once we have that conditional PMF, we can compute the conditional mean of B given A. And we can do that for each of the possible values of A. So let's do that. This is what the conditional PMF looks like after normalizing so that it's actually a valid conditional PMF. In order to compute the conditional mean, we're going to apply our formula for the mean, which remember was basically a sum over the possible values of B. And then we used to multiply by the probability that B takes those values, but now we're interested in the conditional probability that B takes those values, given that A is equal to 1. So we use that conditional probability instead, and this gives us, so these are the three possible values. We multiply by each of the corresponding probabilities, and we get that the conditional average or conditional mean of B when A is equal to 1 is equal to 15 over 7. Now we can repeat this when instead of A being equal to 1, it's equal to 2. Of course, the conditional distribution changes because we're taking another slice of the joint PMF. When we compute that weighted sum, now we're conditioning on A being equal to 2. So those probabilities are going to change. Since the probabilities change, the value of the conditional mean obviously also changes. It becomes slightly larger. Now it's 16 over 7. Let's do that again when A is equal to 3. This is how the conditional PMF looks like when A is equal to 3. We again do this weighted sum, where now we're using the conditional probabilities given that A is equal to 3. Those conditional probabilities are actually equal to just 1 over 3. So when we do the weighted sum, the conditional mean in this case is equal to 2. So that's actually how we define the conditional mean function of a discrete random variable B given another random variable A as this weighted sum of all the possible values of B multiplied by the conditional probability that B takes those values given that A is equal to whatever value we're fixing it to. Notice that this gives us a function of A. So here, if we plug in A is equal to 1, then we get 15 over 7. If we plug in A is equal to 2, then we get 16 over 7. And if we plug in A is equal to 3, we get 2. So that's why we're calling this a function. Strictly speaking, it's not really a function because there are some values that we cannot plug in. So we can only plug in values for which this conditional distribution is well defined. I cannot plug in 23 in this case, okay? But otherwise it is a deterministic function. I plug in a value, I plug in 1, I get 15 over 7. I plug in 2, I get 16 over 7, and so on and so forth. In the literature, you might see a different notation for the conditional mean function. You might see this notation. Expected value of B given that A is equal to A. So this notation is kind of intuitive, but it can also be quite confusing because here we have a function of A. And I felt that this notation doesn't really capture that. So this is why I've decided to use the alternative notation. But you will find this notation in books. So just so you know. Okay, so now that we have defined the conditional mean function for discrete random variables, let's do the same for continuous random variables. The ideas are very similar. So this is an example where we have two random variables A and B that represent the coordinates of an otter, an aquatic animal that is swimming in this triangular lake. We assume that the density of probability of the location of the otter is constant on the lake. So the joint PDF of these random variables is constant within the triangle. It equals 2 because the area of the triangle is equal to 1/2 and it has to integrate to 1, and 0 outside. All right, so this is the joint PDF. And now what we're asking is, imagine that we're standing over here and we see that the otter is somewhere on that line. So we know that A is equal to 0.75, I think it is in this case, but we don't know anything about B. What is the conditional mean of B, the conditional average of the horizontal coordinate given this information? Well, in order to compute that conditional average, we need to characterize the conditional distribution of B given that information. Since B is a continuous random variable, we're going to do this using the probability density function of B, conditioned on knowing that A is equal to a certain value. That is the conditional PDF. If you don't remember this, go to the video on conditional distributions of continuous random variables given other continuous random variables. But I'll remind you, basically the way we compute that conditional density is by taking a slice. So here you have to imagine the triangle coming up like a slab, and then we take a slice of the conditional PDF along that line. Okay, this is the slice. So this would be fixed to A equal to 0.75. Now we have to make sure that that slice is a valid conditional PDF. It gives us valid conditional probability densities. So it has to integrate to 1. So we divide by the integral of the joint PDF along that line, which happens to be the marginal PDF of A. Again, if you don't remember this, go to the video on conditional distributions of continuous random variables. How do we compute that marginal? There's another video on marginal distributions of continuous random variables, but let me tell you, we essentially just integrate with respect to B. So if we integrate with respect to B to compute the density, the marginal density of A, in this case, we're integrating the joint PDF from 0 to 1/2. So just to be clear, we're integrating like this until that line. This is why this line is 1 minus A. If we do that, we get that the marginal is equal to 2 times 1 minus A. I know that I'm going a little bit quickly, but this is not the point, right? So we compute the marginal. The marginal happens to be equal to 2 times 1 minus A, and then we use it to normalize and get the conditional PDF. Again, feel free to review this on your own, but the point is that we're going to use the conditional PDF of B given A, which happens to be constant between 0 and 1 minus A. So it's like a little rectangle. Okay, so now we know the conditional PDF of B given A. We're going to compute the mean of B given A. How do we do that? Well, we use our formula for the mean of a continuous random variable, where we basically multiplied every possible value of the continuous random variable times the density and then integrated that. But now we're not going to use the marginal PDF of B. We're going to use the conditional PDF of B given that A is fixed to whatever value we're interested in. exactly like we did in the case of the discrete random variables, except that there we were using the PMFs. So now we're just going to plug in our formula. We have that we're integrating b times the PDF, which is constant between 0 and 1 minus a. And this integral with respect to b, well, what's the antiderivative of b? Is b squared over 2. This is just equal to 1 minus a squared divided by 2 times 1 minus a. So we have that the conditional average of b given a is actually 1 minus a divided by 2, which makes a lot of sense because basically, I'm going to show you a picture. I should have waited, but I just want to show you the intuition. Okay, so the intuition is we know that a is here. What happens? Well, b is has uniform density there. So what is the average? The average is just this point in the middle. I couldn't help myself. I wanted to give you intuition right now. I think I'm going to show you a picture in a moment. But anyways, so that's why we obtain that the conditional mean is 1 minus a divided by 2. It makes a lot of sense. It's exactly that midpoint. All right, so I derailed the video a little bit. Sorry about that. The way we define the conditional mean of a continuous random variable given the conditional mean function of a continuous random variable given another random variable is exactly using the formula that we just used, where compute this weighted integral, and it's weighted by the conditional PDF of the random variable given the value that we're conditioning on. Okay, so very similar to the discrete case, except that we use integrals and densities. In our case, in the triangle lake, we derived that the conditional mean function is equal to 1 minus a divided by 2. Here again, notice that this is a function in the sense that when we plug in different values of a, we get directly a number. So if we plug in a is equal to 1/2, then we get that the conditional mean function at 1/2 is equal to 0.25. If we plug in 0.1, then we get 0.45, and so on and so forth. Of course, we cannot plug in any arbitrary value because this conditional density, has to be well defined, okay? Otherwise, we cannot compute the conditional mean. So now here is the picture. Again, what's going on here? We're fixing a to be, for example, on that line. The conditional mean is exactly the midpoint of that line. So when a is equal to 0, the midpoint is at 0.5, and it travels down to 0 exactly along this line. So here you clearly see that this is a function of a, where you can only plug in values for which the conditional PDF of b given a is well defined, which are values between 0 and 1. All right, so hopefully that was clear. Now let's turn to the problem of estimating this quantity from data. So imagine that you have a data set where we have samples, joint samples of two quantities. Of course, you need joint samples because we're trying to determine the conditional average of a quantity given another quantity, and for that you need pairs of samples. So we're interpreting these samples as this data as samples, as joint samples from a random variable a that is discrete and a random variable b. And now we want to estimate the conditional mean of b given a. So what do? For example, imagine that we want a conditional mean function of b given that a is equal to 3. What are we going to do? Well, we're going to go and we're going to check how many of these guys, for how many of these guys xi is equal to 3, and then we're going to average the corresponding values of y. Hopefully that makes sense. So let us define the set for which ya, for which of the pairs for which the first entry has a certain value. So here y1 would give us all the pairs for which xi is equal to 1. Y23 would give us all the pairs for which a is equal to 23. So now we want the conditional mean given that the first entry is equal to that value, we just average the second entry, okay? So notice that it's not actually a set if I want to get like very mathematically precise, because there can be repeated values. So we would call it like a bag or a multiset. Okay, so basically the way we compute the conditional mean given that A is equal to a certain value, like 3. We look at the bag of pairs for which the first entry is equal to 3, and we average the second entry. This is the number of pairs for which the first entry is equal to that value. We have to divide by that, and we sum, of course, the second entry. This may be more complicated to explain than to actually just figure out. Let's take a look at an example. So here, imagine that we have these movie ratings. Well, here we have these movie ratings of Mission Impossible and Independence Day. Just to be clear, this is telling us the ratings of this movie and the ratings of this movie given by certain people. So 12 people decided to give Independence Day a 2 and Mission Impossible a 2. Okay, so these are the joint examples. So in this case, the examples are of the form 2-3 or 4-5 or 5-5. Basically, the first entry is the rating that the person gave to Mission Impossible. The second entry is the rating that they gave to Independence Day. So now imagine that we want the conditional average of Independence Day, of Independence Day, given that Mission Impossible is equal to 1. What are we going to do? Well, we average these guys. Imagine that you want the average, and this is, by the way, this complicated procedure that I just showed you is essentially doing just that. Okay, so that's why I said that maybe it's easier to just visualize than explain it mathematically as I did before. If we want the conditional mean, given that Mission Impossible of the ratings of Independence Day, given that Mission Impossible has a rating of 4, boom, we average these guys. Okay, and this is the function that I'm showing you here. We see that on average, when people like Mission Impossible more, they also like Independence Day more on average. There's an interesting effect where people that really like Mission Impossible have a particularly high value for Independence Day. This might just reflect that some people rate very, very highly. Whenever they're a bit happy with the movie, they give a 5. So, but of course, this is just my interpretation. Notice that in general, there's a linear trend, but there is this non-linearity here where suddenly this jumps quite a bit. So as I was talking about, it seems that the rating is particularly high on average for people that gave 5s to Mission Impossible. What about if the random variable that we're conditioning on is continuous? Okay, so imagine that now we have pairs, but this guy is continuous. Can we apply the same procedure to compute the conditional mean function of the second entry given the first entry? Think about it for a moment. The answer is no, because now we want a condition on a certain value of the first entry. Chances are we won't find it in our data set, right? Because this is a continuous quantity that can take any value on a continuous interval. If I want to condition exactly on 2.1, chances are we won't find exactly 2.1 in the data set. So what do we do? Well, there's two options. The first option is that we basically use kernel density estimation or something like that to compute the conditional density of B given A, and then we use that to approximate the conditional mean. Another option, perhaps slightly more pragmatic so that we don't have to compute integrals after we have computed the conditional density, is to basically say, okay, how about I'm not going to condition on A being exactly equal to that. I'm going to assume that the conditional mean function is somewhat smooth. And what I'm going to do is I'm going to just take the first entry to be close enough to A. So I'm going to take pairs such that the distance between the first entry and the certain value A that I'm interested in is smaller than epsilon. Again, I'll show you a picture in a moment that might be that might be easier to follow than this. But essentially, you build that set, and then you take the average. Okay, so this is the number of pairs for which the first entry is epsilon close to that particular value of A. So then let's take a look at an example. Here we have the temperature in Corvallis, Oregon, and Versailles, Kentucky, and we want to obtain the conditional average of the weather in Versailles given the weather in Corvallis. So here you see the points. Things are continuous. This would be the joint PDF computed using kernel density estimation. So we could just basically take a slice of this joint PDF, renormalize it, and compute the conditional mean function in that way. Nothing wrong with that. An alternative is to basically take a small rectangle here of width epsilon. The width that I'm going to use in what I'm going to show you is just 1 degree. And then you average the points that fall inside. Of course, you average the temperature in Versailles for those points. Okay, that's what I meant with the somewhat complicated formulas that I just showed you. If we do this, we obtain this function, which is, by the way, smooth. So that justifies our approach. Although it is a bit noisy here, try to think why it's noisy. And as a hint, I'm showing you the points kind of in gray in the background. Well, here there's very small number of points, so the average is very noisy. When we have more points, the average is less noisy. It shows a linear trend, interestingly, almost linear, between the temperature in Kentucky and Oregon, that is then broken when the temperature is very high in Oregon. Then basically the relationship between Versailles and Oregon kind of breaks down, and here we're not, the conditional mean is actually constant. The conditional mean of Versailles given Oregon does not continue growing. Okay, so I'm no climatologist, but that's kind of interesting. So this is essentially telling us that over here a linear model is reasonable, here not so much. Okay, so what have we learned? We have learned the definition of the conditional mean function, and we have learned how to estimate it from data. Thank you very much.